Welcome back to the channel, everyone. For today, we will be doing a deep dive into what's called an exploratory data analysis or EDA. So in this video, we'll discuss why EDA is so crucial and important to the data science workflow. And we'll also be using a practical data set from the UCI Machine Learning Repository, or UCI stands for University of California in Irvine. Real-world data such as the heart disease data set would be perfect for us to showcase our real-world data analysis, of course, using a range of tools that we will display in this video. So without further ado, let's begin. Exploratory data analysis, or EDA, is the process of exploring data and investigating its structure to discover patterns, relationships, and to spot data anomalies. EDA would then involve summarizing the data with the use of statistics and visualization methods to spot non-numerical patterns. Ideally, EDA should bring out insights and realizations from data that cannot be obtained through formal modeling and hypothesis testing. When done properly, EDA can dramatically simplify or advance your data science problem and may even solve it. A proper EDA hopes to accomplish several goals. 1. To question the data and determine if there are problems inherent in the data set. 2. To determine if the data on hand is sufficient to answer a particular research question or whether additional feature engineering is required. 3. To develop a framework for answering the research question. And 4. To refine the questions and/or research problem based on what you have learned about the data. As you can see, EDA is an iterative process itself. Unlike what most people think, EDA is not a formal process. In fact, it should be obvious that anything with the word exploratory is not bound by strict rules and are therefore non-formal. Rather, EDA is free-form. It is in this stage that you start to chase the ideas you may have and see which ones lead somewhere. Some of these ideas may not necessarily work out, and you can therefore start pursuing or branching from other viable ideas. EDA therefore gets you thinking critically about how answerable your problem is and if it matches your expectations. Exploratory data analysis is generally classified into several ways, such as graphical or non-graphical, and univariate or multivariate. Some references argue that one should do the non-graphical methods before doing the graphical ones. The argument is that doing the non-graphical methods ensures that you become familiarized with the dataset, which makes visualization easier, such as which variables are quantitative and qualitative. Below is an EDA cheat sheet that I have prepared for you guys, and we'll go through them one by one in greater details. Please take a look and examine each of the categories. So first up, let's talk about univariate analysis. As the name suggests, uni means one. So here, we're focusing on one variable at a time. The main goal here is to understand the individual characteristics of that single variable. So first, for the quantitative, we have the histograms, which answers the question, how is our data distributed, or are there patterns, clusters, or gaps? Next, we have the boxplots, where it answers the question, where does the majority of the data lie, and are there outliers? For the normal QQ plot, it answers the question, does the data follow the normal distribution? For the line plots, we basically want to see how the data change over time. And for the bar chart for the categorical values, basically, we want to understand how many instances are there for each of the categories. Now let's look at multivariate analysis. Here, we are examining relationships between multiple variables, helping us explore patterns that just wouldn't be visible when we're looking at a single variable alone. Here we have the side-by-side box plots for one categorical and one quantitative variable. This basically answers the question, how does a quantitative variable vary across categories? We also have grouped bar chart for two or more categorical variables. This answers the question, how do the categories interact with each other? And for two or more quantitative variables, we have the scatterplot, where it answers the question, is there a relationship or trend between the two variables? We likewise can use correlation heatmap, which answers the question, which variables are strongly related? And finally, we can use the Pairplot to answer the question, what are the pairwise relationships between all the variables? For the univariate non-graphical technique, we can look at the location, which is basically just the mean and the median, and it answers the question, what's the average or typical value in our data? The spread, using the IQR, standard deviation, and range, which answers the question, how spread out is our data? The modality, which answers the question, how many peaks are there in the data distribution? For the shape, which is measured by skewness and kurtosis, we want to find out the answer to the question, is the data symmetric or does it have outliers? For the categorical one, we can look at the table frequency. It answers the question, how often does each category occur in the dataset? For the multivariate non-graphical technique, we can look at the mean, median, and spread for one categorical and one quantitative variable. This typically answers the question, what's the typical value within each category? And for two or more quantitative variables, we want to understand how strongly are the variables related. So we want to use correlation and of course covariance, which is basically just provides the same insights as a correlation but is less standardized. So it answers the questions, how do the two variables vary together? While some sources would consider this as part of the EDA process, some sources would treat the following section as data pre-processing and as a requirement for an effective EDA. So for our session, or for this video, let's go with the latter. So before doing the graphical and non-graphical EDA techniques, we first need to do the following. Identify the dataset dimensions. This means how many observations there are as opposed to the number of features or columns. Some algorithms fail to produce the desired outputs, as in optimization problems, when the number of features exceeds the number of observations. 2. Identify the data types. Particularly for Python, EDA methods, especially the graphical ones, work best with certain data types. So while the form of data may appear similar, for example, for numeric columns, some methods would not work if the data type is classified as an object versus that of a float or int. And 3, to identify the target or the output variable. In some of the graphical methods, it will be important to identify the target or the output variable to visualize that particular individual variable. That's also the variable that you will be using to compare across the different categorical and quantitative variables. A good way to accomplish this is to use the .info method of pandas. It likewise provides you the non-null information, which is part of the univariate non-graphical method techniques or methods you should be pursuing. Before we begin with Python, it might be good to discuss the dataset that we will be using in this tutorial or this lesson. So the heart disease dataset is practical for showcasing EDA because it involves health data that can provide insights into risk factors and patient profiles. It includes both categorical and numerical features such as age, cholesterol levels, and more, of course, making it an excellent resource for demonstrating comprehensive EDA techniques. This is found in the UCI Machine Learning repository, And one can access it by going to the website for that dataset repository donated to UCI, or the University of California in Irvine. So as you can see here in the variable, we have age, sex, resting blood pressure, serum cholesterol, and other data that could help us analyze correlations and patterns that may lead to heart disease. So we'll be using this dataset and downloading it programmatically to begin our Python session. So to start our EDA session, let's first import the necessary packages that we will be using. We'll be using Pandas, NumPy, Matplotlib, and Seaborn as well for a more visually appealing chart. So to download the heart disease programmatically, we just need to get this URL, and I'll post this link in the description on the YouTube video, and use the .read_CSV method of Pandas and input that URL in the method as an argument. And with that, you'll be able to view heart disease dataset. Let's see, it really just downloaded the CSV file and it didn't contain the columns. So for this one, we need to input the following columns. So columns are as follows. It's age and sex, basically the one that we've seen earlier. So when we've input this column, we can actually just put it here before the URL. If this is our column or our heart disease columns, right, dataset columns, when we read this for the URL, then we can supply names here and just give the columns variable which contains the column names, and can actually supply other arguments such as NA values. We want to be able to put in, let's say for example, none, and skip initial space to true. Okay, to examine the first 5 rows, use the df.head. So we already know the columns because we have supplied it, but we want to understand the shape, so that will be df.shape. And as you could see here, there are 303 rows with 14 variables here. We also want to check the information about the particular data set. So here you'll see the non-null information. So we have a very clean data set. You can see as well here we have float and we have integers. When we were reviewing it earlier in the UCI ML dataset, there were all of this were actually just classified as integers, but as you could see, the way it was done here, the way it was read here, was actually it was a float, and that is why we gave those instructions or preliminary check that you must be able to perform before you do your EDA, especially for the graphical ones where it will only work for certain data types. So this is the application of the DF info from the reminders we have earlier, especially from the before you do your graphical and non-graphical EDA section of this video. Now, we want to also understand some of the descriptive statistics. So this will be for the non-graphical one. So that would be for df.describe. As you can see here, the df.describe, however, would only look at the numerical or the quantitative variables. So, for example, for age, there are 303 observations, and the mean age of your observation is 54. The standard deviation is 9. The minimum age that was captured in the dataset was 29. The first quartile, or the 25% percentile, is 48. And the way we interpret this is that 25% of your data set has a value that is equal or less than 48 in terms of age. The median value, or the 50th percentile, is that of 56. As you could see, we used to compare median and the mean to assess whether there are outliers. The mean, of course, follows where the position of the outlier is. The 75th percentile, or the third quartile, is that of 61, and the maximum age captured in the dataset is 77. You can likewise see it here. For sex, it was encoded as 0 and 1 as a categorical value. So of course, if you're doing machine learning, we have to do something about this one. But right now, since we're just doing EDA, then we leave it as is. And the same interpretation can be used for all the other columns here. If you want to check the descriptive statistics of those categorical, we will use the command, or include in the argument, include, and here we would put in O. So this command will separate the categorical ones. So as you could see here, you have two, which is the CA and then the TAL. Now, the descriptive stat that falls for the categorical variables are the count, the unique and top, and the frequency, the most frequent one, frequency of the top. So how do we interpret this? There are 303 counts or occurrences for CA and TAL. There are 5 unique categories, but the top value, for example, for TAL, if you look at this one, it has 63733. The top value is that of 0.0, and that value occurred 176 times over 303 occurrences, right? And for TAL, the same interpretation. So we have 4 unique values for TAL. So here, if we look at in our head, the TAL value is so CA is 032. It was actually the TAL that we were describing earlier. And the top value, as we've seen there, is actually 3. And 3 occurred 166 times over the 303 instances recorded in that data set. This is already very powerful for you to ask certain questions for your data set and even to refine your strategy moving forward. So for example, you might be doing some classification, and in classification, imbalanced data set is a big problem. So for example, you'll find out that if the frequency of the top value here is so much farther than so much nearer than the count, meaning that the minority value, let's say for example you're doing just 2 classes, the minority value is very little, then you have an imbalanced data set. Now you have to look into your toolbox and find out what are the techniques that we can do to address this particular problems in our data set in order for our machine learning to be more effective. And that actually is happening while you're doing the EDA. Pandas has a range of methods to provide the other information we want to know, such as maybe the mode, skewness, or kurtosis. So for example, for this particular case, the application of skew and mode and kurtosis will have to be on a column level. So for example, for this particular case, if you want to, let's say for example, get the age and find out the mode, you can apply the dot mode. Okay, so 58 appeared the most if we're treating age like a category, meaning one age is one bin. So bin 58 has the most number of occurrences. But note that mode is mostly applied for categorical variables. So we could also look at, let's say for example, the skewness using the dot skew method. And of course, we can also look at the kurtosis. And one can actually write a loop here to test skewness, kurtosis, and even mode for the different variables. So let's try to write it now. Maybe it's better if we have this at the end. Okay, so there. Maybe to make it appear nicer, we could have a space. Okay? Now, for the IQR, we need to do some calculations. So this is for the IQR. Okay, so you have an error here. Okay, could not convert string to float for the CA. It's a categorical one. So so for the skewness and kurtosis, it only really works for quantitative variables. So what would have been nice is to actually remove here. So let's say, for example, what we could do is remove, and it's a good practice, the quant columns. So the quant columns will be that of all of this except the CA and thal. Okay, so we just cut that, and we have here the cat columns. Okay, there's also a code to do this more efficiently, but likewise do it manually. All right, so now here maybe just put for columns and quant columns, and now there won't be any error. Okay, so for the IQR, the interquartile range, we need to do some calculation. So here we'll have to look at the percentile. So let's say, for example, what's the IQR that we want? Maybe we want as well for maybe for cholesterol. So that would be for NP.percentile. Okay, and here you want to input that particular column, so that will be DF chol, right? So you're saying that you want to divide this into two figures, and that would be the 75th percentile. So pay attention to the syntax. It's list. So you're dividing this one, the first argument, into this percentile. You want to know the 75th percentile, which is the third quartile, and the 25th percentile, or the first quartile. As you know, IQR is simply Q3 minus Q1. Right? The third quartile minus the first quartile. So this will result into two numbers. So that would be 275 and 211. So the first one, because it corresponds to this one, will be Q3. And of course, the second one will be Q1, corresponding to this one. And therefore, your IQR would just be Q3 minus Q1. And the IQR, we can have as IQR for cholesterol, would be this, 64. Now let's go and discuss the univariate graphical methods. For this particular section, we'll be discussing about the histogram, or the histplot, and we will also discuss the Boxplots, which is a very effective data visualization tool, which also has a lot of information about the descriptive statistics that we might be looking for. So for the histplot, let's say, for example, we want to get the distribution of data for, let's say, age. So to do that, of course, one of our best practices is to create first a figure. So fig, and let's say the fig size is 1812. For the histplot, it's actually very simple. It's just sns.histplot. Of course, we'll be calling from the Seaborn package. And let's say, for example, we want our x to be that of the df h. And after this, we don't need to show the plt.show if we have already the matplotlib inline, but just for the sake of this session, we'll use the plt.show. So here, you're able to see the distribution of the variable h. Like what we've seen earlier, you can create a loop for this one. Let's say, for example, you want to create histplot for all the quantitative variable, which is a very effective and easy way for you to visualize all of them. And of course, to get you to ask those questions that we want. So for quant columns, for call in quant columns, Then we want to do this. And maybe we want to also put in here the title. And we put here an F string. And maybe just make it smaller. Okay, so we have the age, we have the sex variable. I think we need to change this. Okay, so age, you have the sex because you only have two values here for the quantitative variable, right? It actually should be a categorical variable, all right? So distribution of stress BPS, draw, and as you can see, you can do that by loop. Okay. If you want, however, to view the kernel density estimate that is going to be overlaid in this particular graph, you could supply the answer true to the argument KDE, which stands for the kernel density estimate. Okay. Oh, sorry, not here. It's not here. It's in the Hisplot. And a kernel density estimate, which is supposed to be estimating a smoother version of the distribution, is overlaid on the chart that is generated. Since we have already discussed what a kernel density estimate is, it's time to create the chart for KDEs. So a kernel density estimate is a way to estimate the probability density function of a continuous random variable. So, of course, it helps to visualize the distribution that we have seen, let's say, for example, earlier, like the age, in a smooth curve, offering an alternative to histograms for understanding data distribution without the binning artifacts that the histograms can introduce. So, of course, it's useful for visualizing underlying distribution of data points, especially when we've seen it already when data are continuous. So, for example, the cholesterol levels that we've seen, and a smooth estimate of the probability density function is desired. Of course, if you also want to avoid the rigidity of histogram bins and capture a more fluid representation of data, KDE would be a viable alternative. So for KDE, instead of Hisplot, we simply will change the argument to KDplot. So in this particular case, KDplot, and let's say, for example, instead of us supplying the x to be just one variable, you could likewise do this. So for example, your data would be the df, and we want to look at, let's say, the variable name of cholesterol. So let's visualize that. Here you have it. And if you want to create, let's say, a loop over this one, you can likewise do what we've done earlier. But right now, I'll be changing the categorical variables here. So let's change here. Sex will now be a categorical variable, right? Because it only has two values. And let's run this again. Go back here. Okay. So it's easier to do a loop if you have this, right? And here. Sorry, columns. Okay, age. Oops, sex is no longer supposed to be there, so. Oh, sorry. It's supposed to be here. Okay, so there you have it. For categorical variables, if you want to count the frequency for each of the category, we could use the count plot. So let's simply just create a loop. So let's say for column and cat columns, we would create first a fit. And there you have it. Now let's talk about box plots, or also called as the box and whiskers plot. They are excellent in representing information regarding central tendency, symmetry, skew, as well as outliers. Now, the only thing they may lack is the information on multimodality. So, let's discuss how we would interpret or the parts of a box plot. The box here indicates the range in which the middle 50% of all the data lies, right? So this is the interquartile range, which is Q3 minus Q1. Therefore, this box here contains 50% of all the data. Now, the lower end of the box is the first quartile, so in this particular case, and the upper end is the third quartile. Between Q1 and Q3 is the interquartile range. We've calculated that earlier in the non-graphical portion. Now, in the box plot, the solid line indicates the median. So this one is the median, the 50%. So if we have the descriptive stat from the df.describe method that we have done earlier, then the 50% there is the median. And the dashed line indicates the mean. So it's also found in the df.describe. Now, the T-shaped whiskers go to the last point, which is still within the 1.5 times the interquartile range, meaning it would be, for example, this would be the maximum and the minimum if there aren't any outliers. If there are outliers, this value would just extend to 1.5 times the interquartile range. So this value here times 1.5 would be this value. But if there are no outliers, or if the maximum value is within the 1.5 times IQR, then the whiskers would extend to that maximum value. Now, points that are further away are considered extreme values or outliers. So let's do box plots, or a box and whiskers plot in Python. Just like hisplot and countplot, for boxplot, the syntax is quite easy. So let's create a loop, and this will only be available for the quantitative variables. So as we've seen earlier, concepts such as the median, the IQR were all present in the df.describe for the quantitative variables. So, if you want your box plot to be in horizontal form, this is how you do it. But if you want it standing or in vertical form, you just change this x to y. And there you have it. So we're seeing some outliers here for the tres BPS and for the cholesterol. So there are outliers. Okay. Now let's go over the combination of a categorical variable and a quantitative variable. So for this one, we will be using the bar plot. So for a bar plot, we have to remember that the x-axis or the y-axis, one of the axes is a category, and one of the other axes is that of a quantitative. If it's just the count, then we call it the count plot. So for this one, let's create a loop. This will be the loop that we need to see all the possible combinations. Okay, so there you have it. So in this particular case, The height of each bar represents the mean or the average value of the quantitative variable for each of the category. So for example, for this case, if 0 is for female and 1 is for male, then we know that the cholesterol is a bit higher on average for female if that is sex equals 0, and the average for male is a bit lower. This approach allows us to easily see which groups have higher or lower average values in comparison to others. Now, by summarizing data in this way, you can quickly interpret and make data-driven decisions or hypotheses about differences across groups. So this is for the sex group. And okay, so now we're able to see some insights right on the spot. So for example, for this case, the exang variable, there is a significant difference across the sex groups. And if we go for a different, let's say, category here, now we're going for the CA, we're also seeing some difference, and that might get you to ask some questions and, of course, refine your data science approach, whether, for example, for modeling. And that might also give you some idea of whether or not that variable might actually be influential or predictive in your formulation of the model when you're deciding which feature to involve. Like for example, if you've seen here in certain cases that, well, the particular average values doesn't really differ across groups, then maybe that's something that you could possibly remove if you want to reduce your dimensionality. But in cases where definitely there is a greater variance across categories, that might be something worth looking for. So this is a loop that we've done simply to ensure that we're able to try all the possible combinations, okay, of the category and the quantitative variable. So if you want a more descriptive visualization of a categorical variable versus a quantitative variable, instead of a bar chart, we can use the box plot. So far, we have seen that one of the most useful visualization for descriptive statistic is that of a box plot. Of course, it might not be easy for people to interpret that, but for us, analysts and data scientists, box plot may easily be something that we could definitely use to spot patterns. Now, the good thing about this one is that this code that we have written for the bar plot can simply just be tweaked in order for us to have the combination of the categorical and quantitative variable and the box plots across each of those category values. So we just copy this one, and for this one we just need to change this one for the box plot, and we have to remove the confidence interval because box plots don't have confidence interval, and we run this. Voila! It's that simple. Now we could see, therefore, if there are significant differences. We've seen certain age earlier to be the same for the bar plot, or not that much different. But if you look at this one, the median of the sex equals 0 is a little bit higher than the median of sex equals 1. So looking at all the different possible combination of quantitative and categorical, we'll be able to spot now that, hey, there are certain outliers, for example, for the THALAC, values for each of the sex. And of course, if we move to other categories, you'll definitely be able to see which ones have more variance, and for example, which ones have different distributions, which are of course very powerful in designing the particular data science experiments that you have. In fact, just by reading some of these box plots, you may be able to have some findings already as to which influences your target variable. We may want to visualize 2 or more categorical data because so far, we've just been comparing one categorical and one quantitative variable. We may want to compare 2 categorical and a quantitative variable to see how the values differ across those categories. So this is done through Seaborn's Catplot, or a Catplot. So a Catplot is a powerful tool in Seaborn for visualizing relationships between a quantitative variable and multiple categorical variables. It allows, of course, for flexible plotting options for Barplots, Boxplots, and is very useful for comparing distributions or averages across different groups. So because we are having two categories here, the loop that we're going to do will have to be changed slightly. Well, it has to be more complicated. So let's do that now. So in this particular case, our loop becomes more complicated because we need to bring in two categories. So now we have an inner loop within our inner loop, and we have to avoid comparing the same category with one another. So we have to put this condition in. So there you have it. The x argument first represents the categorical variable. So here you see the categorical variable, and the u here represents the second categorical variable. So we know how they differ across the y value here, the quant, right? So for example, when we were doing the bar chart and the box chart, we needed a quantitative variable to somehow represent across those categories. So the colors, or the U, is one category, and then the x-axis is one category. So you could separate this. And here, it allows for a more complex and, of course, deeper analysis of the comparison of the values across these categories. If you want to change this, for example, and you just maybe want a bar chart, and as you know, the bar chart will just simply give you the mean or the average, then you could just do this. So it will give you the bar chart. Or if you want the violin chart, then you can do this. So it's just a little bit, well, taking longer for the violin chart, but technically you can use the violin chart. This type of visualization is useful when you're analyzing interactions between two categorical variables in relation to a quantitative outcome, of course. And it might help you identify patterns, disparities, and maybe some insights across groups. And there you have it. So you could now check and explore the insights that you're able to get with this chart. Now let's discuss how we can compare two quantitative variables. So the plot to use when we want to do that is a scatter or scatter plot. It's used to examine, of course, relationship between two quantitative variables. So it's actually very useful for identifying trends, clusters, and of course outliers. If you have outliers, a single point would be so far from the rest of the group. So in this case, we could write a loop to explore all the possible combination of our quantitative variable. Okay, so there you have it. But notice that when you have something like this, where the scatter plot seems to be forming a horizontal or vertical line, that's a very good indicator that, for example, if it's a horizontal line, your y-axis here should be treated as categorical variable. So a scatter plot is really effective if you have something like this. So if you're getting something like this one, then even though dfinfo is saying that this is an integer, then it should to treat that as a categorical variable. So we know that rest ECG seems to be better as a categorical variable. Same with CP, and what else? If it's like this, right? where it's a vertical line, X here, CP, should be or is better treated as a categorical variable. Now, instead of doing the loop that we have done earlier, if you want to explore simultaneously all of the possible combination of the quantitative variable, then we could use the pair plot in Seaborn and do something like this. S in S.Pairplot, and the input here is a data frame, and you have to ensure that only the quant columns are included. After that, we could input here that the diagonal here is what we want to be a KDE, or a kernel density estimate. And of course, the title is supplied by okay. So here it is a grid, and for each of the off-diagonal cell, meaning not part of the diagonal, this shows how the two variables relate, of course, helping to find potential correlation. So, for example, how you read this, this is for the scatter plot of CP and H. This is the scatter plot of the target and H and the slope. So there's a y here. All the y variables are found in the, or the y-axis is found, of course, here in the y-axis, and all the x-axis are found here in this x-axis. Now, the diagonal here that you're seeing is the kernel density estimate of H with H and CP with CP, and the tres BPS with tres BPS. So instead of doing what we were doing earlier, where we were doing the loop, you can simply just do this. But of course, the benefit of the loop is that you're able to have more granular control if you want larger charts or if you want to save them. So the last multivariate graphical chart or visualization that we will discuss is the correlation heat map. So the heat map usually represents the correlation matrix using color gradients. So let's say, for example, we'll use cool warm. It will be used to display positive and negative correlations with different color. There's also the color scale, where the color intensity and the hue would indicate the strength and the direction of the correlation, with, of course, as we know, correlation just ranged from -1 to 1. So the code for that would be this, but please note that for the correlation, we only just use that for the quantitative variable, because the correlation coefficients that it's being represented by the heat map, or the Pearson's correlation, measure the strength and the direction of the linear relationship between two continuous quantitative variables. So categorical variables typically don't have meaningful correlations in the same sense, so they represent distinct group rather than continuous values. So since we have already the quant columns here, right, that we were using earlier, then that's we can create a heat map using that. So it's just this. Oh, I guess where we're, the error is here. There. Okay. So there. So the lower the value, the colder the color is. So it's a little bit blue, and then the higher the correlation, the redder, the closer it is to the color red. Okay. So there. So I guess this is where we made the mistake. The minimum, the value of the minimum, and the value of the maximum. Alright, now that we're done with the multivariate graphical method, let's discuss the multivariate non-graphical method. So this might be useful for cases like that when we were comparing two categories and we wanted to know how their quantitative how a quantitative variable differs across those categories. And while we do have box plots for that, we might want to see that in numbers, right? So in that particular case, we want maybe to pursue a non-graphical option, and the code will be something like this. And there you have it. So for example, for sex equals 0, we have 97 count, and the mean is 55.72. So how this differs with the normal describe is that we first grouped it according to the category. So here, and so this is for the sex category. So we have the CA as well. And it might be better for those who want a written or an exact number rather than just the visuals. Of course, for the covariance and the correlation, you could simply just create something like this for the DF core, and you'll be able to see that. Notice that the categorical columns are automatically removed, but of course not the sex part yet, because we know that it's still classified as an int. And if you want it to be the covariance, you just use the cov method. Okay, so there you have it. So that's it. We've successfully completed this EDA crash course. Now, here are 3 key takeaways on the goals and benefits of exploratory data analysis, or EDA. Number 1, confirming data types and correcting misclassified variables. We've seen how EDA was able to help us, like when we were doing the Scatterplot, to identify whether we have misclassified a variable, whether they're categorical or quantitative, despite what or how they are encoded. So identifying and correcting misclassified variables is actually very important in order for us to ensure that we won't skew any correlation or regression analysis. Number 2, we were able to understand data distributions, and we were able to detect outliers. So EDA enables us to explore the distributions of each variables, which includes patterns, central tendencies, and spread within the data. And finally, for number 3, we were able to reveal the relationships and initial hypothesis generation. So EDA allows us as well to explore relationships between variables through visualizations like the scatterplots, correlation heat maps, and pairplots. While we tried to make our tools and methodologies complete, the list that we have is of course in no way comprehensive. For example, geospatial and temporal feature requires different EDA principles and processes that should be explored when necessary. Regardless, data scientists should not be afraid to add and explore more, as the purpose of EDA is to gain familiarity with your data and advance the research problem at hand. And there you have it, everyone. With all these EDA techniques, we hope that you could explore your data more effectively, uncover hidden insights, and better set you up for the modeling process. Till the next video, bye now.